All right. Welcome back. We have a very exciting afternoon tutorial session. Actually, this one is especially close to what I think about every day. So very excited to that NVIDIA is presenting on their, I think now maybe a year or so collaboration with the battery company called SES and how they have adapted reasoning models for science. So look forward to Kristopher and Carmelo covering that. So without further ado, over to you. And it's tutorial format. So again, right, please feel free to interrupt, ask questions. Right, we want it to be, we want it to be interactive and useful for everyone. So with that, floor is yours.
Where do you want to introduce you? Sure. Hey everyone, my name is Carmelo. I'll be giving the second half of the talk, but I'm a solutions architect at NVIDIA, and I'm here with Kristopher. Is it on? Okay. Oops. Hey everyone, my name is Carmelo. I'm a solutions architect at NVIDIA. I'm here with Kristopher, and we'll be giving this talk together.
All right. Hello, everyone. Yeah, Chris Keipert, solutions architect from our higher ed and research team. And just to give a little bit of context, so our solution architect team works with researchers at university, national labs, helping port, optimize, or in other ways enable science on accelerated platforms, right? So we have a lot of individual PI conversations about things like, again, porting, optimizing, matchmaking to different libraries or different hardware that might be most appropriate for the problems that you're facing. So great honor to be here on the stage today and sharing some of the collaboration work with SES AI. All right, so we can, get a little bit in the weeds here, but in terms of our agenda, I'm going to start a little bit by motivating some of the intersections between generative AI and science, because of course, right, as we think about these reasoning, it's really an extension of these, foundational generative AI paradigms that have been, taking the road by storm over the last year or two. So we're going to very briefly preview through some of the offerings on the NVIDIA side, and then I'm going to turn it over to my colleague Carmelo, who's going to be going in a bit more of a deep dive in the specific SES AI collaboration and talked about how they were able to adapt a large language model for a really important reasoning application for battery research. All right, generative AI for science. First of all, it felt a little bit old school even to put this on a slide without the word agent or reasoning attached to it, right? It seems almost, it's really taken us by storm. But let's kind of take a step back and look at how generative AI has really transformed the computational science landscape and see how we're using the results of those applications to again feed into these reasoning models that can tackle new problems for us. Okay. So in terms of the modern supercomputer, right, we typically classify it into 5 separate workloads, 5 paradigms that we're seeing really. Over to you. Yeah, sure. How's that? I'm not sure about the top one. Good. Okay. Beautiful. Okay.
There's like a hide meeting control.
Beautiful. Awesome. Yeah. Good heads up there. So, right, certainly in the simulation space, if you think just, 20, 25 years ago, there were approximately 0 GPU accelerated simulation applications, but now it's a stalwart, right? There's several thousand. Me, I have a background in computational chemistry, so, molecular dynamics, right? Oil and gas applications are almost a de facto standard. But what we're now starting to see, obviously, with generative AI, even for some of those really high demand computing applications, are being replaced wholesale by things like, OpenFOAM, right? If we move out from the center a little bit into simplest AI and digital twins, right? This is in that kind of in-between field where, we have a simulation component and an AI component working together. And, it allows, the laws of physics or mathematical reasoning or whatever to actually bound the progress of that generative model, right? So it's very, very important space. Think of things, for example, Kaushba will be speaking about Physics Nemo, where you can, for example, take a, Fortran 77 application that you've been using for 30 years and start to replace and do surgery on some of the PDE solvers and tap into, AI in that way. And then certainly on digital twin, it's just an extension of that, right? In the visualization space, right? And there's a huge generative AI component as well. If you think about things like frame interpolation, and then out to kind of more emerging schemes such as quantum computing and edge computing. So all of these are being massively impacted by generative AI, right? And if you look underneath the hood of all of these different paradigms, they actually look pretty similar, right? Look at the GPU. It's good at matrix multiplication. It's good at dense linear algebra, right? And underneath the hood, there's a lot of BLAS, a lot of cuBLAS, LAPACK. But we know a bit more about these workloads to the point where I encounter fewer and fewer CUDA programmers on a day-to-day basis, right? Because there's more domain-specific libraries that you can kind of bubble up and use as a researcher and kind of drop in without as much effort. So I'm going to touch on a couple of these as we lead into how some of these simulation tools, again, were used to develop our reasoning models. Oh, okay. So Carmelo is primarily going to chat about the NeMo framework. Has anyone here used NeMo before or played with NeMo? Okay, certainly, yeah, Alex's group. So NeMo is kind of our foundational framework for large language model training. So we're going to talk about domain adaptation and how that's extremely important for these scientific reasoning models. Again, Kristopher is going to talk about physics NeMo, which from the name, right, it's physics oriented AI surrogate models, right? So again, getting into replacing PDE solvers with AI surrogates and whatnot. And then staying with the theme of material science that we've been having this morning, I'm going to touch a little bit on two of these frameworks that are highly relevant for AI-driven discovery, those being BioNeMo and Alchemy, right? Alchemy is the one that was used by SCS AI. Okay. So if you pretty much talk with any university, what are the top AI and inference workloads? Many folks are running AlphaFold, right? OpenFold. The field of drug discovery has been absolutely revolutionized by AI, right? And that goes from the academic level to the industry level on really all different paradigms, right? From structure prediction, protein ligand binding, even give it a seed molecule of some a ligand with known activity and generate 1 million compounds with similar activity. And again, many of these things were traditionally done with simulation that are now being replaced with these AI surrogates, right? So if we look at the foundation of why this is such a successful field right now, it's because of the awesome work that everyone here is doing, right? If you look across the universities, across the startups, things like AlphaFold, right? Bolts, which now extends to RNA and protein structure prediction, Neuroplexer, DiffDoc out of MIT, right? There's a community around models here and that are, opening these up, throwing up on Hugging Face, and then folks can take those and, take it on your internal data sets if you're, for example, a pharmaceutical company, and, get additional value on your own unique data there, right? So I just wanted to touch on that. Now, in terms of NVIDIA's contribution in this story, right? So each of those models that you saw on the previous page, we've taken those and we've encapsulated them in something called a NIM, or a NeMo Inference Microservice. Okay, essentially, NVIDIA, we have a whole army really of material science and folks with domain-specific knowledge here, and we're also very good at inference, right, and high-performance inference. So we've taken those community models like OpenFold, AlphaFold, DiffDoc, et cetera, and optimized them and containerized them, and then shared them with the world, right? So you can take those same open source models that you may have been using, download the NIM container, and run, at very, very high speed through our inference solution. Okay, so that's kind of the main piece. On the left there, we also have an entire training framework. This is domain specific for the biological space, where pharmaceutical companies, for example, can take these models off the shelf with these NIMs, and they can add their own special internal experimental data, right? Or information on ligands that they may have, as their important IP, and fine tune the model to incorporate that additional knowledge, right? And then finally, I will briefly show a blueprint, right? So you have all these NIMs that are kind of different pieces, different, an AlphaFold here, a DiffDoc there, but in isolation, they don't do a whole lot, right? They're actually supposed to be composed into pipelines, right? So if you think of virtual screening, for example, right, there's the ligand generation, there's the protein folding, and then binding them together, right? So how do those actually compose together? Okay. Just to give you an example for these NIMs, for example, here's AlphaFold 2. Anyone here run a lot of AlphaFold 2? Yeah, AlphaFold users. Okay, so if anyone's familiar with AlphaFold, there's a, obviously it was one of the big models that came out pretty early. There, a Nobel Prize, or not too shabby, but actually a substantial amount of AlphaFold is CPU bound, right? So there's a really important step called the MSA, mean sequence alignment step, which, as I understand, there's like some server in Taiwan or some like academic group, right, where they have like the CPU bound server setup that handles that MSA step, and that's traditionally been a bottleneck when folks are running inference on AlphaFold. And I've actually heard of universities where they're hitting AlphaFold so hard that they actually get rate limited on that server and are no longer allowed to do the MSA, right? So For example, with our AlphaFold NIM, we took that MSA step, which again was a CPU-bound application, and ported it to GPU, right? So now you have a complete end-to-end GPU accelerated AlphaFold model, which you can download and start running on your GPUs. Okay. And then finally, I just want to come back to this generative virtual screening model. Again, we're really heavily investing in these blueprints, which show, scientists, you can kind of take this off the hood, see how these models compose together, right? And then adapt it for your own domain, right? Adapt it for your own specific workflow. So here's an example, again, for virtual screening, where a user has a protein folding component, which may have been traditionally done with something like molecular dynamics in the past, is now replaced with AlphaFold. Molecule generation, right? A lot of RD-Kit in organic chemistry, right? Handwriting to figure out good ligands can now be done with things like MolMIM, generative models for molecule generation. And then once you have the ligand and the protein, you need to bind them together, right? Maybe in the past you ran, over at Oak Ridge on a bunch of summit hours doing AutoDoc. Now it's almost instantaneous with these AI facilitated models. Okay. So I just wanted to quickly show for anyone in terms of interactive. So if you go to build.nvidia.com, you can actually pull up these NIMs very much like a ChatGPT like interface. So it's a pretty messy web browser or web page, but if I scroll down here on the left, there's a biology section. Okay. And then I could, for example, choose OpenFold. And this is that OpenFold NIM model that I described earlier, running on DGX Cloud, right? Running over in the cloud somewhere. I can put in some protein sequence. Very likely this one is cached. Run generate. It's sending the request off to the server, folding the protein for me, running the inference. There we go. Nice and interactive. Isn't that cool? Right. And extending all the way to those blueprints that I described. For example, here's a generative virtual screening blueprint where, again, you have some protein that you're folding. Here's the MSA step. You're interested in binding some ligands to this protein, so you give it a seed molecule and ask it to generate some, additional candidates. And then once you have those, you need to bind it together. So I could click generate here. It takes about a minute, but you can see here, again, this is all AI facilitated, complete end-to-end virtual screening workflow. The protein was folded, the ligands were generated, and they were docked into these poses. AI every step of the way there. Great. All right. So let's move over into material science space, where obviously there's the biology is a forefront. I think even last week I saw OpenAI. They said that they're now supporting like tool calling out to RD-Kit. I don't know if folks are following like Future House, but they even have like these LLMs that you can interact with for like retrosynthesis pathways. Absolutely amazing, right? As a computational chemist, very near to my heart. But moving over into material science space, we see very similar as well, right? There's massive databases of data sets of properties, structures that are being released. I would say computational chemistry was one of the early adopters of AI plus HPC, specifically in MLIPs or machine learned interatomic potentials, which can give you very, very high accuracy at very, very low computational cost. So again, a very, very hot field. So NVIDIA has something called Alchemy, and this is what was used by SES AI, leading into Carmelo's discussion here. Alchemy is our framework for AI-accelerated chemistry and materials, right? And as Venkat pointed out, right, there's so many different kind of paradigms or different ways to inject into chemistry where AI can really make a big difference, right? From low-level electronic structure theory, atomistic simulation, over to molecule and materials discovery. And emerging, right, formulation optimization. We heard quite a few folks even today talk about things like mixtures, and then again a little bit more future looking, but again, Future House isn't perhaps in the future on synthetic route and reaction optimization, right? So a platform, again, don't have to worry about CUDA. You can interact at this level as a chemist and get a lot of value out of the AI. Okay. I'm going to talk really, really quickly about what SES AI used. And this is, again, on the simulation side. This is really about getting the data to feed into the large language model and reasoning models, right? We need billions and billions of molecules, properties. And if you look at traditional computational chemistry today, even for those folks who are kind of ahead of the curve and using these machine learned interatomic potentials or, kind of dabbling in AI, that runs on GPU just fine. But very often the actual computational chemistry program, the NW-Chem or GAMES or Gaussian, is very often running on CPU, right? So even though you get to tap into the niceness of this MLIP, just that back and forth between the CPU and GPU really limits the performance that you can achieve, right? So under Alchemy in collaboration with SCS AI, we actually were able to incorporate a batch geometry relaxation, right? So doing the structure optimization technique on the GPU, right? Along with using the MLIPs. So now the entire solution is end to end on the GPU. You don't have to worry about data transfer back and forth from the CPU. So that already gives a really, really large speed up. But perhaps the more important thing here is we, again, with SCS AI, also added capabilities for batching, right? So anybody here do much molecular dynamics by any chance? Any MD, Gromax, Gaussian? Okay, so one thing you'll notice oh, there we go, beautiful, Amber. If you look at molecular dynamics, you'll very often notice that it's just kind of tickling the GPU, right? These things have been so optimized over the last 15 years that even for a really substantial chemical system, the GPU may be just ticking at 4 or 5%. And we see something similar in the material science space if you have very small molecules, right? And small molecules are important, right? I know that the person next to me in grad school spent, a 50+ year career studying hydrogen or studying hydrogen, right? So small molecules matter, but they barely utilize the GPU. So one thing that folks have noticed is you can actually take many of those jobs, ensembles, right? Very important for molecular dynamics, and stack many, many jobs on a single GPU running at the same time, right? So instead of running one job and barely utilizing the GPU at all, maybe you're throwing 50 or 60 of them, right? And through aggregate, getting a really, really large speed up. So that's exactly what was done here with Alchemy for the SCS AI folks. So you can see where these NIMs, again, for that BGR is batched geometry relaxation. And then we also have a batch DFT, density functional theory microservice, which can be applied for property prediction as well. And this is just one component in the blueprint, if you will, for SCS AI, right? So again, this is about data set generation, which can then be fed into things like different ranking models, candidate prediction, and then even interacting with a chemistry LLM front end, right? So it's a piece of the puzzle, but simulation is foundational, and this just shows some of the contributions in the material space. And yeah, the speed ups. I mean, 800x sounds crazy, right? And it's again because of that batching. Okay. So with that, I'm going to turn it over to Carmelo here, to talk about reasoning. I just want to say, when we think about reasoning, and I don't know if folks have watched, for example, the GTC keynote, but it's really about this center section here, right? It's about this RL feedback, basically having a game or a quiz that the AI model, can have some idea of what the goal is and try its best and get feedback. And that RL reinforcement loop. Reinforcement learning loop is really what causes all the amazingness of these reasoning models. But that's a ton of computational expense, right? And knowing what the right answer is still going to hold simulation very, very core to the heart. So definitely, very foundational. Keep these advances in mind on the simulation side. And with that, I will pass it off to Carmelo.
All right, so from here, we'll start talking about how we actually perform this domain specialization of our large language models, specifically for these scientific tasks where we'll focus on two models. One that's called ChipNeMo, which as the name suggests is an internal model to NVIDIA for chip design, and another model called Omniscience, which was developed in collaboration with SES AI for battery related tasks. So just comparing ChipNeMo and Omniscience from a super high level, we have ChipNeMo here on the left, and some of its workflows that we use to do this domain adaptive training include domain adaptive tokenization, and we heard a little bit about tokenization earlier and the importance that plays in training our models, and we'll dive into that in more detail later. ChipNeMo has a domain adaptive continued pre-training step, which is just this kind of general knowledge incorporation of a large corpus or pool of data that we have for our particular domain. And then finally, ChipNeMo has this model alignment with domain-specific instructions, where we further fine-tune our model into something more similar to like a ChatGPT style interface where we can interact with it and ask it questions about our particular domain. Omniscience on the right-hand side builds from the ChipNeMo workflows, and it adds a reasoning distillation step. So we incorporate this sort of thinking into our model, and we can use it for more complex scientific tasks that involve breaking down the model into these individual subproblems that can be solved and reasoned upon. And so I'll take the Omniscience workflow and dive into the pieces from a little bit of a higher level. And then from there, we'll go and look at each individual component of the pipeline in quite a bit more detail and discuss some of the practical ways in which we can do each step. So the Omniscience training pipeline that I was just describing, it started with the LLaMA 3.1 70 billion parameter model that is open source, we can use, and that's what we start with as our base model that we then incorporate our domain adaptive pre-training workflow, which consists of taking a large corpus of data, which in this case is 35 billion tokens of scientific literature across various sources, which I'll describe in a moment, and continually pre-training our model until it gets to what we call the Omniscience base model. And this base model is a domain adapted model already, which has information that has been incorporated from this large pool of data that we've collected. So from the base model, we move on to the model alignment stage, which is, again, making this sort of like chat-like interface where we're aligning our model to our specific domain further by giving it these task instructions, which could be something like multiple choice questions, summarization, and those sorts of tasks, and having our model learn to further improve its capabilities in this particular domain. And this is called the Omniscience chat model. And then finally, we tag on this reasoning distillation phase, which involves incorporating reasoning into our model by way of distillation. And I'll cover the specific way in which we do that in a little bit. And finally, further on, I'll cover how this reasoning model was used in a battery agent framework. So the first step of doing this domain adaptive pre-training is essentially collecting our data. And so this is going to be where we pull data from various sources, which could be, from the internet, could be from archive papers, it could be Chem Archive, PubChem, things like this, and just downloading basically as much data or collecting as much domain-specific data as we can. It doesn't necessarily have to be data that's labeled right at the moment, but just getting as much data as we can to essentially use to train our model. And a really important part of this process is going to be the data processing. And we'll talk a lot about our data processing pipelines using NeMo Curator in a further section. And so specifically here for the Omniscience workflow, there's 19 million raw documents, preprints, and textbook entries that were pulled. And after the curation pipeline, which does things such as deduplication and some various filtering, that's reduced down to 17 million unique documents that are then used for the continuous pre-training of our base LLaMA model. And this was done using the NeMo framework, and the result here is the Omniscience base model. So the Omniscience base model, like I was mentioning,
on the previous slides, before we jump ahead, can you talk a little bit about sort of how those, how did they, or who selected that that data, and like how did this work in this collaboration? I'm assuming this was with SES, right?
This was with SES.
Yeah. So how? Can you share a little bit about? Like how did they find the raw papers, or like what was the process? Did you work with publishers to get publishing agreements? Like what was the?
Sure. I don't know a lot of the specific details on that. I wasn't an author on the paper, and so I don't know exactly. Geetika can answer.
Yeah, so in getting the tokens from all the for doing the domain adaptive pre-training, so SCSAI, they worked with the publishers, and they took a lot of open papers that were already available, which had permissive license to be used for doing tokenization and for training. So I think a lot of it was just open papers that were available. They picked and they selected which chemistry publications that they want to use. Yeah. I know that is like always the hardest problem. Like, how do you find permissive license to use? Yeah.
And it's in a format that.
No, so they had to tokenize it. Yes, so they used, I think, structure IO at that time because some of the features in the Nemo framework were not data curator were not ready. But now, like if you have to do it now, we would use the data curator. So so in doing the tokenization, the data prep, the essays helped in doing that step. Yeah.
Perfect. And we'll see a little bit more about the data set breakdown and where specifically papers came from in a further slide. So we were moving on to what we can do with the base model that has been continually pre-trained on this large data set. And this is where we get to the supervised fine-tuning on instruction data set phase. And for Omniscience specifically, what we used here was a randomly selected subset of our large set of 19 million documents where we pulled out 50,000 documents and used a foundation model. In this case, it was GPT-4o Mini, to essentially build a data set for us that was generated by asking our model to create 4 task instructions per document. So we have 50,000 randomly selected documents. We ask GPT-4o Mini to create 4 task instructions per document, and then it's things like question answering, multiple choice questions, reading comprehension, and summarization. And taking those 50,000 documents with 4 task instructions, we get 20,000 documents, and we save out 40,000 of those to use for the evaluation and add 160,000 of those to this data set that we'll use for the supervised fine-tuning. Now, at this stage, it was important for the team to essentially incorporate an additional 90,000 chat instructions from a general purpose open source data set to ensure that our model didn't lose some of its general capability with kind of like everyday tasks, and to ensure that it stays sort of grounded in like this reality of, people are going to be maybe using this for general purpose tasks as well. And so after performing the supervised fine-tuning here, what we're left with is, again, this chat model. And finally, we moved on to the reasoning-based knowledge distillation stage. And so at this point, we took the S1K 1.1 data set, which is derived from DeepSeek R1 traces on scientific tasks in, I think, physics, mathematics, and maybe one other. And essentially what this data set consists of is questions and answers given to DeepSeek R1 about these tasks that are related to some specific domain, maybe math or science. And the data set itself is a style of supervised fine-tuning where the question leads to an answer that has the reasoning trace from DeepSeek R1 as its sort of answer. And so this is the way that we're incorporating this reasoning ability into our Omniscience model, is by training directly on these reasoning traces that kind of show our model how to reason and think about complex problems. And so this is in contrast to the other style of incorporating reasoning, which is by directly learning how to reason through reinforcement learning, which we heard about this morning. And so in this way, we can kind of piggyback off these larger models that already know how to do this complex sort of reasoning step and just take their data directly and do another supervised fine-tuning of our model. And so the output here is the Omniscience reasoning model. And briefly, I'll talk about this example of this reasoning model's use case in a dual agent framework for ranking and explainability of materials. And so the application here was to essentially take a molecule and feed it into this dual agent framework where we had Omniscience acting as the generator model, where it would essentially give us an answer to what sort of properties a particular molecule would have. And if we're looking at a specific task, it could tell us whether or not this molecule might be best suited for this task. And with that answer, we fed it into a reflector model or a critic, which in this case was a GPT model. And essentially, these two models would act would work together to refine a solution space that we started with to then grade molecules based on their ability to perform well at a task or based on these properties that we were looking for specifically. So with that high level overview, I'll now dive into each of the components that we just talked about, from curation all the way through the reasoning phase, in a little bit more detail and give you some practical examples and information about how you can go about doing these things. So first, we'll start talking about data curation with NeMo Curator. So NeMo Curator itself is NVIDIA's sort of pipeline for doing this curation, and it contains predefined utilities for all steps of this pipeline, essentially. So we always start by downloading our data from these data sources, which could be dispersed across the internet, or maybe we have a lot of data locally that we want to process. Data Curator, NeMo Curator allows us to ingest all of this or write utilities to essentially do a web crawling and downloading all of these documents. And so after our data download and extraction phase, the first step that we want to do is essentially clean up our documents and remove things that could be problematic for our model in the downstream tasks. So we would want to remove things here like Unicode errors, or if some of our documents have a different language than the language that we're trying to train our model in, we would remove some of those kind of documents. And so the first stage here is just a basic cleaning and pre-processing stage. After this cleaning and pre-processing, we can move on to a bit of a deeper level quality filtering, where we use some heuristic filters that can take out things such as super long documents that have contextually irrelevant information based on a heuristic that we've defined, or it can remove excessive punctuation. And so this document level filtering helps to clean our data even further. After this stage, we move on to a deduplication stage, where we can do exact deduplication, fuzzy deduplication, and semantic deduplication. And so this is really important for just taking out a lot of these documents that may literally be the exact same but come from different sources, or have information that would be, that could bias our model towards one particular answer in a solution, or just making sure we have unique documents here. And throughout, okay, so we'll move on to the quality filtering piece as well. And this is where we can add in some NeMo Curator custom filters. And so in this stage, specifically for Omniscience, they included a personally identifiable information, a PII redaction step. So after collecting all these papers, they remove things like names, emails, addresses, other information that might be sensitive. And at this stage, you could include any other sort of custom filter that you want. So if you were looking at code, for example, you could remove really long lines of code that may be irrelevant, or you could remove comments or something like that. Here in this stage, you can also introduce some small sort of classifier model, which may be a neural network that essentially compares your documents to documents that have been labeled as high quality and documents that have been labeled as low quality, and just do an additional filtering step here. So just to highlight some of the impacts of these various curation modules on model performance, there's a short sort of a toy example here where a 357 million parameter GPT style model was trained using the Common Crawl dataset, which is kind of like a general web dataset. And at each stage of the curation pipeline, we evaluated the model on its downstream task performance. And so by starting on the left side here of the figure, we can see that a model trained with just the raw data set has this sort of baseline performance with an accuracy of 47.5% on whatever the downstream task may have been. I actually don't know in this case, but it starts out at about 47.5%. And then each additional bar here in this histogram represents an additional step of this curation process. So after that initial text cleaning, where we're removing things like languages that we don't expect to be present or Unicode errors, we see a little bit of a boost in performance in our model. And then by adding the deduplication step, we get an even bigger step up in our performance. And then finally, with this final quality filtering stage, we get an even larger improvement in our model's downstream performance. And I think it's important to note at this stage, you can't necessarily expect this to work exactly in the same way for whatever model you're training or whatever data set you have. This is just an example of how these modules can be applied to boost your model's downstream task performance. And as just a very brief kind of example of a snippet of code that you might expect from Nemo Curator and using its Python API, this essentially shows the steps from downloading a data set, running a sequential curation pipeline, which contain some built-in classes that you can use from Nemo Curator, and then finally just executing the curation pipeline. So by using Nemo Curator, a lot of these that are shown up here are pre-built into the Python API, and they can just be applied straight away to your data set. And this is where you can also include some of these custom modules that you can implement based on following the base classes and add them into your curation pipeline. So it's very modular, flexible, and easy to use. So again, just to go over what the data set reduction looked like for Omniscience, we started by downloading the data set, performing some of these deduplication quality filtering stages, adding in the heuristic filtering, and finally, it resulted in our high quality data set, which had 2 million less documents than we started with. And then this is what we use to feed into our custom tokenization pipeline, which I'll talk about momentarily. And let's just briefly cover some of the dataset sources and distributions for both ChipNemo as well as Omniscience. So we have ChipNemo on the left-hand side, and in the top left corner there, that's the data that we used for the continual pre-training for the ChipNemo model. And so here we can see that a large percentage of the data is essentially related to documentation surrounding chip design documents. Another large percentage of this training data is design source documents as well. And so we can compare that with the Omniscience continual pre-training data, which is on the right-hand side. We have the majority of the documents here coming from Semantic Scholar, peer-reviewed literature, and archive papers. And so I'll come back to this a little bit later, but these bottom two figures here show the supervised fine-tuning data that we use for ChipNemo and Omniscience as well. And so what's interesting here is that in the ChipNemo dataset for supervised fine-tuning, 128,000 of its samples are publicly available samples that come from some of these general purpose datasets. And we only use 1,400 samples that are domain specific. And in this case of ChipNemo, these domain specific examples were essentially created by a human expert. And so we had, there were actually people who were verifying these samples or creating them. And that's why there's such a low number of samples here. And this is in contrast to Omniscience, where I talked about previously, we used a model itself to create 160,000 samples that are domain specific that our model could learn from. And we incorporated these extra 90,000 samples, which were sort of general purpose. And so the balance of data here is interesting to compare across both models. Okay, so with the data curated and processed, we're ready to talk about custom tokenization, which can be a very important part of the pipeline. And we heard about this a little bit before, but what I'll dive into specifically is some of the both performance improvements that you can get in terms of the throughput of your model, as well as some of the accuracy gains that you can get as well. So some of the goals, just in terms of like why we want to do custom tokenization, it can improve the efficiency of the tokenization process on our domain specific data. And I have a really cool example of that on the following slide. And essentially what this can do is it can lead to minimizing the effort and the resources that are required into doing this continued pre-training and supervised fine-tuning of our models. But the downside here is that our models might actually lose some of their performance on their general purpose tasks, and it might be harder for us to converge our models onto our domain-specific data. So as a really cool example, which actually comes from the e-commerce domain, is with this example from eBay, where they trained an e-commerce domain-specific model for listing title generation based on, essentially data that they had collected. And what they did here was they used a custom tokenizer to train their model, which they created themselves, the tokenizer, and they based their model on LLaMA 3.1 8 billion. And so what we can see just by looking at the figure here is that the throughput of their listing generation has a really large throughput improvement over the base LLaMA model. And to understand why that may be, we can look at a very specific example of how custom tokenization is being applied. And the example that they use here is in tokenizing the word Yu-Gi-Oh, which Yu-Gi-Oh is kind of like a card game, I guess. But it's very specific because a lot of people like to resell Yu-Gi-Oh cards online. And so when we tokenize this word with the base LLaMA tokenizer, it would break it up into 4 individual tokens, meaning that our model to reproduce the word Yu-Gi-Oh would have to do 4, steps essentially. But with the custom tokenizer, this word Yu-Gi-Oh is represented by 1 single token, meaning that we essentially get a 4 times improvement in its throughput for representing this word. And so this leads to just that overall efficiency improvement in the listing title generation. Similarly, when we look at some results from ChipDemo with its custom tokenizer, we don't see as quite impressive gains in the efficiency that we get from tokenizing. But when we look at these 5 specific data sets that were used with ChipDemo, we do still see a certain percentage improvement over our original tokenization performance. And so when we're performing custom tokenization, there's always going to be this trade-off. And so we essentially want to understand how many tokens to add based on our domain-specific data and what can happen if we include too few tokens or too many tokens. And so it's important to find this balance between adding the new vocabulary and the performance that we're after, where a large number of tokens can maybe lead to higher improvement on our domain-specific data, but it could take a long time for our models to converge. And too small a number of tokens can essentially just leave us in the same place that we started with our base model. And so this example from Trillion Labs shows the performance of a model that they trained with the custom tokenizer, and they were looking at the Korean vocabulary. And so they essentially used different number of tokens in their tokenizer and just plotted out the performance of their final models on their downstream task with the varying level of vocabulary size. And they found this sort of sweet spot in between a very small number of tokens and a kind of excessively large number of tokens, which actually really reduced their model performance. And so the steps to create a domain adapted tokenizer can essentially be summarized with the following. Step 0 here, which isn't up here, is basically you need a domain-specific data set to start with to train your custom tokenizer.
Okay, we'll get into details for that. Are there any questions so far?
Carmelo, I do have a question about the tokenization process that you shared earlier, along with model architecture. How do you account for the heuristics-based filtering? How do you account for biases and errors in the quality filtering process?
Yeah, that's a good question. I mean, you can implement these kind of heuristic filters in whatever way that you deem necessary for your particular data set. And so it really comes down to what your preference is in implementing those. But some of the things that I mentioned earlier could be like removing excessive punctuation. And if you're looking at code-related tasks, removing lines of code that are super long, things of that nature.
Sounds good. Thank you.
Other questions?
I've been paying attention a lot lately to this fine tuning idea, and you mentioned that you give it new data, new information, domain specific, that the existing model forgets what it's already learned. That's a bit bothersome to me to a certain degree, right? That doesn't happen to us, right? Does this problem go away the bigger the main foundation model gets, or is that always present at roughly the same level? And what can we do about it, right? Because that's really bad.
Yeah, that's a great question. I guess to talk a little bit about the first part of that, some of the ways that we try and overcome this problem of forgetting, or people like to call it catastrophic forgetting in our models, is we like to backfill this domain specific data with general purpose sort of common data that would be used for training your base foundation models. And so that's where the addition of these samples in both the Chip Nemo and the Omniscience supervised fine-tuning stage come in, where we have our domain specific, task construction data set, but we pad it with data that comes from these open source, task construction data sets that are general purpose and commonly used. So it kind of helps keep our model grounded in this sort of, it helps our models just not forget these things that it's learned. It's also, I'll talk about it a little bit later, but it's important to remember that when we're doing supervised fine tuning, our training dynamics are a little bit different than when we're doing this sort of general purpose continual pre-training stage as well. And so we need to, from a very practical kind of engineering standpoint, we need to implement the various mechanisms that are used to prevent things like overfitting and forgetting. I don't know exactly how to answer the second part of your question about, with the larger models, is this a bigger problem and that kind of thing? I think a lot of that comes down to just empirically learning and studying how these things happen.
Instead of fine tuning, could, for example, retrieval augmented generation or just a knowledge graph? Let's say I work at a synchrotron lab, for example. I would like to have beamline assistants, for example, who understands roughly the general science and has documentation and could guide somebody new who's not necessarily understands all the technical things. Maybe it's someone who just comes with a sample, perhaps just through a rack or a knowledge graph, just do the same or a better performance.
Yeah, that's another fantastic question. I'm actually addressing that later as well. But a lot of these sorts of techniques and technologies like RAG or in-context learning, they're complementary to each other. And so if you have just this kind of one-off use case where you only want to use your model for a little while on one particular thing, it could be better just to use RAG or to use in-context learning to kind of, tell your model, hey, this is what I want to focus on for an hour. Let's do this, crack it out, and then I can get back to whatever I was doing. But when we have these use cases, such as the one with SES AI, where they're really interested in doing this kind of long-term big data exploration on a long time scale, where they're not just using the model for an hour or a day or a week even, they want to be able to go back to it a lot and use it. That's where a lot of this domain adaptive training comes into play, where we're actually building a new model to do a specific task for a long time and for a very specific purpose. And at that stage when we have a domain adapted model, a lot of like I mentioned, these technologies are complementary. We can tag on RAG. We can have our RAG piece pulled back from this corpus of data that we pre-trained on if we want to just make sure our models are getting the correct information. Or as new information comes into play, we don't want to continually fine-tune our model with more resources, then we can use RAG in that scenario to pull new information and have our model already be rooted in the science, but be able to give these contextually grounded responses.
Just one last question. It's about agents. Do you have like support for like agents on top of the AI, for example? I would like each agent to be specialized in certain techniques, for example, instead of having to just fine tune the big one, just have it more generalist and just have spawn more specialized models, and they would probably spawn tools, for example. Do you support something like that?
I mean, absolutely. I think that sounds like a great use case for these types of models. Again, something I'll touch on a little bit later, depends kind of on your task at hand too. If you have something super narrow focused, you can train a lot of these, you can fine tune a lot of models with a small parameter count, less than 3 billion parameters for a model to do a very specific task. And you can have 5 or 10 of those go do some agentic workflow for you. It really just comes down to the use case that you have at hand in your particular data and what you're trying to accomplish.
Thank you.
Yep. Okay. Okay, so I'll briefly just talk through the practical steps of creating your domain adaptive tokenizer. So like I mentioned, you need your data, and then you need to actually train the new tokenizer on this domain specific data. Step 2 is going to be identifying your new domain tokens from comparing this domain adapted tokenizer that we just trained to our base tokenizer. And then you take those two and you kind of combine them together. And then you apply the extended tokenizer, which has our new domain specific tokens, to our domain specific data set. And then essentially to avoid this problem and keep in mind this balance of only taking the most appropriate tokens, we apply a sort of empirical cutoff to remove any of these really low count tokens that don't really get used in our domain specific data, but may have come from that new tokenizer. And we just filter them out. And then essentially what we're left with after that stage is our final domain adaptive tokenizer, which has only the appropriate number of tokens, additional tokens that we would need for our domain to fully represent it and have this balance of throughput and increased representation of our data. So now I'll talk a little bit about this domain adaptation and domain adapted pre-training in general, and answer again some of these questions that actually just came up. So one of these questions that we just had is why do domain adaptation in the first place when we can just use RAG or in context learning? And basically that's the answer that I just gave. We want to do this for these projects that have long time horizons, or where we're going to be reusing these models a bunch over and over. And we don't want to essentially lose any of the information that we would otherwise be feeding our model for it to learn or to use with RAG. And so domain adapted pre-training can basically lead to these adaptations to different tones and styles and formats of our new data. It could be really useful for better generalization to our new domains with increased accuracy in handling edge cases. And we can also add in various levels of complexity here by adding in this reasoning phase, which we talked about. And so it's hard, again, to, comes back to another question, because we have to balance the addition of this new data with catastrophic forgetting and becoming too domain specific that our model just becomes useless for anything else. There could also be potential biases introduced by our domain specific data that we weren't aware of, that our model may pick up on and then latch onto, which we may not want. And then there's a lot of new things here too. Like we need to look at how to do data curation appropriately. We need to sometimes learn new frameworks, and it can be a lot to learn. And so that's kind of why domain adaptation is useful, is just to help expand the capabilities of our models here. And so here's a very specific example that comes from the ChipNeMo work, where this set of results represents, it comes from just the domain adapted model of ChipNeMo. So this was without any additional supervised fine-tuning stage. And let's just start by focusing, we can focus on just like this left-hand side, left collection of bars here. And so there's 4 bars kind of per sub histogram here, and this left-hand side represents design, and that's going to be the design task here. And each of these starting bars represents the base model in which our ChipNeMo model was continually pre-trained with. And so here we have LLaMA 2 7B, 13B, 70B, and then on the far right of each kind of sub collection is going to be a GPT 3.5 model for comparison. And then the little toppers to each of the bars represent the improvement that we get from the domain adapted model. And so just looking at this left-hand side again, we can see that with this very first bar here, which is our LLaMA 2 7B model on the base with the topper representing ChipNeMo 7B, we're essentially outperforming GPT 3.5 on this domain-specific task of chip design. And so this holds true across all of these other models that are 13B and 70B, with an increase in accuracy coming every time from our domain adaptation step. And as we start to look at some of these other collections of tasks here at the bottom, the one thing that remains constant is that by using a domain adapted model, we are always getting an increase in our performance on the particular task. In some cases, we're beating or outperforming GPT 3.5, and in a lot of cases, we're on par with GPT-4 as well. But the moral of the story here with showing this full collection of tasks is that you can't necessarily, have a super large performance gain for every single task. It comes down to what data you're using for your domain adaptive pre-training. And so just talking about domain adaptive pre-training in general, there's a lot of different strategies that you can use to go about doing this process. And that's why we at NVIDIA provide these playbooks for domain adaptation, so you yourself can build your own ChipNeMo or Omniscience. And so essentially what we have here is just a collection of recipes or playbooks that you can use to build your own models and pick and choose some of these techniques that work best for you. It's important, I think, I really like this quote here. It says, in general, that the same recipe, it may not generalize well to all model families. And so, you're not guaranteed to get any of these performance gains. It really comes down to picking and choosing what might work best for you and experimenting. So let's talk a little bit about this supervised fine-tuning and alignment stage. And this is where we're essentially, fine-tuning our models with this task instruction style data set. And so some of the common challenges for getting this supervised fine-tuning data is that it could be regulated, it could be hidden behind privacy laws, and a lot of the data could be duplicate, noisy, or inconsistent. Pretty much all the time, there's not just going to be a nice data set that's labeled for you, and so you might need to get a human expert or find some crowdsourced way to label your data. And the data that we're collecting for supervised fine-tuning generally won't be as diverse and may contain biases than our standard data sets. When looking at specific domains like legal, our data could be fragmented by the jurisdictions. In medical and across all domains, really, there's going to be different jargon that our models are going to have to learn. And in some cases, multimodal data might be necessary for our models to really understand the topics at hand. In the service and kind of e-commerce space that we were talking about earlier, you're going to have customer-specific data with some words that are a bit more abstract than we're used to, or our models are used to. And in engineering, we're typically looking for this high accuracy data. I touched on this a little bit earlier, but in this stage, our training dynamics change a little bit because we're using different loss functions, and so it's important to keep that in mind as well. And so some of the ways that we can do this data generation for supervised fine tuning are highlighted here. We talked about the reasoning model-based method that we use for Omniscience, in which we used a reasoning model to essentially generate task instruction data sets based on a subset of data. And this method is very versatile and it works for a lot of tasks, but it's a lot less interpretable. And there's no kind of correctness guarantees because our models can, hallucinate or get things wrong sometimes. If we're doing a code related supervised fine tuning, like for a coding task, something that's common to use is the abstract syntax tree. And this gives you some guarantees on syntax correctness. And this is very interpretable and controllable, but it's not very flexible and it relies on the specific language in which you're using. And finally, we talked about with ChipNemo how they generated their supervised fine tuning data set by human labeling, essentially. And so this essentially leads to very verifiable and high quality data sets that are tailored exactly for our use cases and very specific, but it takes a really long time to generate this because somebody has to actually label the data, like a person has to do this. And the data set sizes are often much smaller. So some of the key technical learnings just from this section and the ones before, when supervised fine tuning, it's best to start from a domain adapted model if you're trying to do a domain specific supervised fine tuning, and using a domain adapted tokenizer leads to better performance in general. We'd like to, as we mentioned before a few times, balance out the domain specific data with this general task data to keep our models kind of grounded in reality of like these general tasks. And then keeping in mind just our loss, our training dynamics are changing, and it's easy to overfit to a small amount of data with these large language models. And so preventing things like overfitting by using early stopping and cross validation and these sorts of techniques is super important. From the evaluation stage, kind of similar to our data sets, you get the best evaluations by using a human in the loop. And so you get these really accurate domain specific feedback if you have someone available, but it's slow. And so we can also use an LLM as a judge, which is common, but again, our LLMs can sometimes hallucinate. They may not be as reliable and they're pretty sensitive to prompts. And so there's things to balance in the evaluation stage as well. And so finally, before talking about some end-to-end use cases, I'll dive into the reasoning-based knowledge distillation just a little bit more. And so again, this is where, for this particular set of examples, our reasoning-based knowledge distillation step is essentially just one more stage of supervised fine-tuning, where we have a very domain-specific data set that has questions and answers, and these answers have these reasoning traces from foundation reasoning models themselves, which we can then just use to directly learn how to reason in our smaller models. And this, again,
Quick question. So you were starting with a high quality data set, then piping that through DeepSeek, and then getting the traces. Is that what you're saying?
Yeah, so in this particular example, the S1K 1-1 data set is a supervised fine-tuning data set that has questions and answers, and those answers are generated from DeepSeek. And so,
questions.
Say that word.
Questions are generated how?
The questions. So the S1K data set, I don't remember exactly where it originated, but it's a collection of scientific and mathematical questions that have been created and answered. It's a pretty small data set. If I remember correctly, I think it is a human generated one. And so we're essentially training our downstream model on these traces. And something that is actually interesting to note here is that the original S1K dataset uses Gemini traces for to teach our downstream model reasoning. But when they were performing these experiments, they found that the traces from DeepSeek actually led to better performance and better incorporation of this reasoning step into our models as opposed to using the Gemini traces. And so the models that we're using to get our data from for incorporating this reasoning through distillation matter as well. And just some of the trade-offs in general for adding reasoning to our models is that we're going to have higher token generation for a given query, just because we're basically making our models think more deeply about these questions. And also along that same line, not all questions need to be reasoned about. Some questions are just standard yes, no. And so by having our models think super deeply, it can potentially be a waste. But reasoning, again, it leads to increased performance in our domain-specific tasks, increased factual accuracy, and the ability to combine and explain complex ideas. So here's just a collection of results from Omniscience, as well as eBay's use case on domain-specific benchmarks with reasoning models. And so let's start by looking at the top left histogram here, which shows the comparison of Omniscience reasoning model to other models in its same parameter class, where we're kind of defining the parameter class as any other model that's between 10 and 100 billion parameters. And so on this GPQA Diamond benchmark, which is essentially like a graduate level test of science and mathematics, we can see that our Omniscience reasoning model is outperforming every other model that we benchmarked in its same parameter class. And this is including models like these DeepSeek R1 distill variants, as well as the base model that we trained from, which we would hope to beat. Moving on to the bottom left histogram here, we can see that this is a comparison of Omniscience reasoning on battery-specific tasks, and this is compared to some of the larger proprietary models that are reasoning models. So we're looking at things like Claude and Gemini, the GPT family. And in most, if not all cases, we can see that Omniscience reasoning is performing just as well, if not better, than some of these models that are way outside of the Omniscience parameter class. And so these domain-specific models are performing much better. They're more efficient, and they can just be more reliable than some of the off-the-shelf proprietary models. The final use case here is going back to eBay's e-commerce model. Something interesting to note here is that the models that they train for their domain-specific task, they do have a little bit less favorable performance on a general purpose benchmark. So this is MMLU. It's kind of like a multimodal language task where our performance of our domain-specific model is a little bit less than the base model that we started from. However, when we look at the e-commerce specific task, it widely outperforms the base model in which it was fine-tuned from. And so now I'll briefly just go through some end-to-end use cases here just to highlight how we can use these reasoning models and just kind of talk through, just at a high level, the steps that I have covered. So this is essentially showing the end-to-end Omniscience workflow. So on the far left, we're starting from a large corpus of data. From this example, it's peer-reviewed literature, archive, chemarchive, these sorts of things, textbooks, and we can split our data set into some benchmarking data, as well as select a little bit of data to use to generate a supervised fine-tuning data set. All of this can be facilitated with NeMo Curator. And after we have our collection of domain-specific data, we can tokenize it to create a domain-specific tokenizer, and then use this for all of our downstream sort of fine-tuning stages. So we do this domain-adapted pre-training, supervised fine-tuning, and then finally this reasoning distillation step. And in this example at the bottom, we're again using this sort of dual agent framework where we have Omniscience acting as this sort of property prediction model. And we have this critic LLM, which is providing feedback to Omniscience. And this is screening molecules coming out of a generator model, which could be, just popping out molecules that are potential candidates for the particular task at hand. And so this kind of represents the full end-to-end workflow that you could use to build something like Omniscience and then use it in practice. This is the example that was shown previously, and what I want to dive into here specifically for just to showcase a cool piece of this workflow is this data visualization piece down here in the workflow. And so again, this was for building the world's largest battery material database, where we use things like NVIDIA Alchemy, which we showcased earlier, as well as our chemistry LLM to rank candidate materials. And I'll showcase some of this data visualization. And so what SES AI did with this massive data set that they had of theirs is they created a map of the molecular universe for these battery materials. And what this is they created this map by using an NVIDIA accelerated version of UMAP, which kind of puts our various material or molecules into clusters that we may not fully understand. But when we filter our map based on specific properties that we're looking for in a material, we can start to see these sort of individual clusters pop out to us. And so everything that is in this figure up here that is colored with green or yellow are all materials that were filtered based on the same property. So we were filtering for a very specific set of things, and the green and yellow is what popped out. Everything that is in the green sort of streak on the bottom left here is materials that have been studied already. So whether that be in the literature or maybe they've been made in a lab, but they have been studied. Everything that's in yellow is a material that has these same properties that could, in theory, be studied. And so what you can do with something like this molecular map is you can kind of look and browse around these various regions and pick and choose molecules to study. Or if your language model is suggesting one of these materials to look at, you can go back to the map and reference where it is, maybe in comparison to the green materials, and look at the various materials. And so I think something that's really cool is that this map and this workflow that we've showcased has actually been used to create new materials in the lab already. Just to wrap up with a few practical best practices if you're actually doing domain adaptive large language models. The work on data curation isn't really ever complete. New data sets pop out all the time. There's these 5 key components that we talked about: data curation, tokenization, pre-training, instruction tuning, and reasoning-based knowledge distillation. Some very practical things. Job crashes will definitely happen, so save frequent checkpoints. But if you are saving frequent checkpoints, just know that if you haven't done that before, they take up a lot of space. And so, you could run through hundreds of terabytes of data. And when we're performing domain adaptation for large language models, if we have a very specific use case, it may be best to use a smaller model, something less than 3 billion parameters. If we're looking for something more general, more than 7 billion parameters is generally a good starting point. And finally, NVIDIA itself offers a bunch of resources for all the things that we've talked about here today. So NeMo Curator and the NeMo framework in general are all available, which can help you do this data curation and all of the stages of training that we talked about. We have a bunch of blogs. The papers that we were talking about are referenced here. And then there's also a NVIDIA DLI, which is a Deep Learning Institute course for domain adaptive pre-training specifically. And so I recommend you check those out. And with that, I'm happy to take any more questions.
Fantastic presentation. Hello, Kristopher.
For the presentation. I have a question in terms of how is this Omniscience actually work in
in the battery, like as in the electrolytes applications, because as I work on batteries, and what we found is most of the time you have a specific target that you want to calculate. For example, homo-lumo for the molecules, and essentially you can screen those molecules using your normal supervised machine learning model. So I want to ask, like, how does Omniscience is in this? How does it work in this sort of workflow specifically?
Yeah, that's a great question. So in this workflow specifically, how you would interact with Omniscience is you would ask Omniscience to either screen an incoming molecule from a generator that we kind of talked about a little earlier. So we could say screen this molecule for based on these properties, and based on the contextual information that we've trained it on, it has knowledge of what it may be a particular property for a battery material that you're looking for. We say we want to look for this in this molecule. Help me kind of screen all of these and rank them based on their efficacy as a battery material based on this property. And so we kind of interact with it in that way of like asking it to screen molecules and interact in that dual agent framework as well to iteratively provide feedback on that.
Is it correct to understand that basically what used to be sort of the supervised machine learning model is replaced with this large language model to get to predict these properties that we want?
Right. Yeah, I think that's a fair way to think about it.
Okay. All right. Thank you.
So one question I have, not directly related to what you talked about, is how do you approach kind of conflicts of interest as someone who's kind of talking about potential benefits of AI, but also as someone who represents NVIDIA, who of course has financial interest in AI? How do you approach that?
It's a great question. Well, I think personally, I think AI has the potential to help push science beyond where we currently are. And to me, that's what's interesting and engaging about all these conversations. I think that if we don't take advantage of the tools that we have at hand right now, then realistically progress is either going to be slower or not made at all. And so by talking about these topics, working in this industry, and engaging with AI in the way that we are, I think it just makes it opens doors for a lot of people, and I think it ultimately benefits the scientific community.
Thank you. Thank you for patiently answering that question. I think it's a theme that we will revisit at least a couple of times tomorrow and day after. Maybe until last year, it was cool enough to show that you could do something. And now it's cool enough to like show that, you can move slightly beyond what current tools can. But I think soon the question would be, so what? How does it impact this particular discovery? But I think that's coming. Yeah, but we can't take it for granted. Other questions? Yeah, so, go ahead.
I think there's a clear tendency now to make models by design more interpretable, maybe including neurosymbolic approaches to formalize the knowledge graphs or whatever representation of the domain that's at hand. So I was wondering if there's efforts in your group to move in this direction.
Yeah, that's a good question. I think in general, yeah, there's efforts to include more of this like very specific domain knowledge into these types of problems. For example, with physics-informed machine learning, that's super popular, and we'll hear a talk about that very briefly. And so yeah, these efforts are ongoing.
So you made a whole bunch of choices, right? And you converged on some best practices, but it's very much dependent on the problem. And this maybe sticking to the battery electrolyte work. When did you start? When was that particular thread started?
September 2024. Yeah, so the customer started working on this in September 2024. So yeah.
And then I think the reasoning aspect was probably after DeepSeek, right?
So the first thing they did was the AimNet 2. That was the first thing that they started with. And then they were working on the reasoning model. They started working on the reasoning model probably, I would say, November timeframe. Yeah. And then DeepSeek blew up in January, in Feb. Yeah. So they have not done the distillation. Like if you see, like their Omniscience model is still the 70B. They have not like reduced the size. So they have not done that. Yeah.
Right. Yeah. So my question was leading into that, right? So there's so many developments happening on the fly, right? So is it even possible to say these are best practices given things are evolving? So what kind of metrics to use? Is it just validation set, or is there something more profound that you use to make those choices?
Yeah, that's a great question. I mean, yeah, as things evolve, I think the state of the art kind of results that we're seeing now may be used as baselines for whatever comes next. One thing that I think is really fascinating that is actually a real world outcome of this is that molecular map that I was just showing, and how it has actually been used to create a material today that is actually like a physical thing. And so some of these sort of outcomes are a way to essentially validate, the choices that we're making and how they're applicable to real world problems.
Yeah, I think that's very good. And I think for all of us, I think it is something to keep an eye on, because same time last year, capabilities that everyone had was order of magnitude less, right? So even though there's still so many things to fix, I think the rate at which things are advancing is just incredible. Even your groups, just go back to 1 year ago, and even our groups going back to 1 year ago, we almost had nothing. So yeah, it's incredibly exciting to see where things are headed. And I can't speak for all of the universities of Michigan, but one of the goals that we have here is to get this kind of workflow injected into several research groups across campus and try to see, what kind of models come out, and maybe even how do these models, when these models start meeting each other, what happens at those intersections. So I think it's incredibly exciting. Thank you for laying out a blueprint and open sourcing it. Any other final questions? All right, if not, let's thank the speakers again for a wonderful presentation.